In this lesson, we will solve a classic thermodynamics example and visualize each step. We will compute the change in entropy for an ideal gas going through two stages. First, an isothermal expansion at 300 Kelvin that doubles its volume. Second, heating at constant volume from 300 Kelvin to 373 Kelvin. Here are the given values. Read them with me. Pressure P1 equals 1.02 times 10 to the 5 pascals. Volume V1 equals 0.005 cubic meters. Temperature T1 equals 300 Kelvin. Specific heat at constant volume, C sub V equals 12.6 joules per mole Kelvin. The gas constant R equals 8.314 joules per mole Kelvin. The final temperature is T2 equals 373 Kelvin. To build intuition, let us see a piston cylinder model. On the left is a closed cylinder. The gas is in blue. The piston is the gray plate. Stage 1, isothermal expansion at 300 Kelvin. The piston moves to the right and the gas volume doubles while the temperature stays the same. Stage 2, constant volume heating to 373 Kelvin. The piston is held fixed while we add heat. The temperature rises, but volume does not change. Entropy is a state function. That means we can add the contribution from each step. For an ideal gas, the reversible entropy changes we will use are: for isothermal expansion, delta S1 equals N our natural log of V2 over V1. For heating at constant volume, delta S2 equals NC sub V natural log of T2 over T1. The total entropy change is their sum. First, we need the number of moles using the ideal gas law at the initial state. N equals P1 times V1 divided by R times T1. Substituting the numbers gives approximately 0.204 moles. Now compute each entropy change. Delta S1 equals N our natural log 2, which is approximately 1.18 joules per Kelvin. Delta S2 equals NC sub V natural log of T2 over T1, which is approximately 0.56 joules per Kelvin. Therefore, the total entropy change is about 1.74 joules per Kelvin. Let us also picture the path on a pressure-volume diagram. We will mark the initial state, the point after isothermal expansion, and the final state after heating at constant volume. First, the isothermal curve at 300 Kelvin from V1 to V2. Then, the vertical isochoric line at V2 as the pressure rises with temperature. Summary: we computed the moles from the ideal gas law. We split the process into an isothermal expansion and an isochoric heating. We added the two entropy changes. The total change in entropy is approximately 1.74 joules per Kelvin.